Hello everyone, I would like to welcome you to the introduction to this course on embedded C programming as part of the online lectures in the Bachelor of Science in Electronics Systems at IIT Madras. I am Nithin Chandra Chukka and I will be giving most of the lectures for this, possibly supplemented by some other specific demonstrations from other members as well. So this course is about embedded C programming. It is meant to take you into the details of how we program embedded systems. So what exactly is an embedded system? What do we mean by programming an embedded system? All of these are questions that we will soon be addressing. And of course, given the fact that we are talking about C programming, there is an assumption here that you have already completed a basic course in C programming to start with. Now, why exactly are we using C for this course is something that I will be talking about a bit later, but the assumption is that you do have some background in C programming before you start this course. So, we will start with an introduction to embedded systems in general, and what better way than to start with the dictionary definition, right. So, this is what I picked up from the Cambridge Advanced Learners Dictionary and Thesaurus. What do we mean by an embedded system? So, it is a noun, it is in the domain of computing, and basically what it says is it's a computer system that does a particular task inside a machine or a larger electrical system. So, this actually requires a little bit of thought. The word particular over here is important, and that is a large defining characteristic of what we have in mind when we talk about embedded systems. What I mean by particular in this case is it's not a general purpose machine, right. So, particular as opposed to general. We are talking about something which has a very specific type of task to perform, and it is going to take that task and essentially repeat that as many times as required. The other thing that I want to draw your attention to is the term inside a machine or larger electrical system. Typically, the embedded systems, the word embedded itself means something that is embedded inside something else. In this case, usually what we mean is this computer system that we are trying to design is going to be embedded inside some other machine. It could be a machine, it could be another electrical system, it could also be another computer by itself, right. But there are certain characteristics that come about when we say that this is addressing a specific particular task inside a larger system, which allow us to optimize and design these things in a different way than what we would design for a regular computing system. Hence the word embedded, and what we will be looking at as we progress through this course is how do these systems differ from general purpose systems, and in particular what does that mean for the way that you program them. So, there are a number of characteristics of embedded systems. The first and foremost is what we call dedicated functionality, that is to say they are not general purpose. So, essentially this is in contrast to PCs or personal computers which we assume are general purpose computers. The whole idea of getting a computer is that it can carry out a number of computing related tasks, right, and in general you have the confidence that given some knowledge of programming you should be able to make it perform almost any task that any other computing system can do. Now, that is not what an embedded system is meant for. Embedded systems usually have very specific functionality wired into them. When I say wired into them, it is done in such a way that it is either put into the memory of the system or into some other configuration which is not trivial to change, right. So, changing the behavior of the embedded system is something that requires going into the details of how it has been built and modifying things that you are not normally given access to, right. Now, another important characteristic of embedded systems is that many of them have a requirement of what is called real time operation. Now, real time is an interesting word. Very often colloquially we use the word real time to mean something is fast. That is not actually what real time means. Real time just means that within a constrained time limit, right. So, very often what you will find is that real time constraints in embedded systems are talking about number or time durations on the order of milliseconds. That is, you need to respond to some kind of a stimulus within a few milliseconds or so. And in the context of a computer, a millisecond is a very, very long time, because after all, when you are working at a speed of more than 1 gigahertz, it means that a single clock cycle inside a computer is only 1 nanosecond long, which means that 1 millisecond is actually a million such clock cycles. So, real time, in other words, does not necessarily mean fast. What it does, however, mean is that there is some kind of a time constraint on how fast you need to respond, and if you do not respond within that time constraint, there is usually some kind of a penalty associated. It could be catastrophic failure, like the entire system, the airbag does not deploy, the car crashes into something, the brakes fail to catch, right? Or it could be something a bit more simple, such as skipping a video frame and getting poor quality of video. Either way, real time means that you have a time constraint that you need to meet when you are implementing such an embedded system. So, let us look at the components that typically constitute an embedded system. How do we build up an embedded system? As you might imagine, and as we will be seeing throughout the rest of this course, a core, or probably one of the most important components, is going to be the microcontroller. And a lot of the course is going to be talking about microcontrollers and their behavior in some sense. Right? But just a microcontroller by itself is not sufficient. You also need some kind of sensors and actuators, right? And typically these could be things like a temperature sensor, it could be a pressure gauge, it could be something else which detects the ambient light, right? And you would also have actuators. So, an actuator could be a relay, a switch, or it could be a motor that actually moves something, or it could be a linear actuator that actually causes something to move, but not in a rotary fashion like a regular motor. Either way, these kind of actuators and sensors are how the microcontroller is sort of talking to the outside world. And of course, tying it all together is the software, right? So, unless you have the software, you can't really do much with just a microcontroller and the sensors and actuators. But once you put all these together, what you get is a system. And by system, what we mean is everything that is involved, right? You need the hardware, you need the software, you need the algorithms, you need the right kind of sensors, you need the right kind of actuators. And an example of an embedded system that comes out of this is possibly a fitness band. In this case, what we have shown is an Apple Watch, right? And it has a number of different functions. Among the more useful ones are, of course, hopefully showing the time. But the rest of it is things like measuring your heart rate, measuring the oxygen content in your blood, measuring the number of steps that you have taken, right? All of those are very specific kinds of functionalities that are sort of baked into the behavior of the watch. And as a result, what we get is a complete system. So, when you do system level design, there are a lot of things that you need to keep in mind. You need to choose the right kind of microcontrollers, you need to choose the right kind of sensors and actuators, you need to write the right kind of software. But on top of that, there are also many other things which are not related to the technology at all, or rather not related to this aspect, the electronics aspect of the technology. That could include things like what material to use for the case, what kind of material to use for the band that is used in order to connect a person, what battery should be used inside this system, and how long is it going to last, right? So, when you design a system, there are many more questions that need to be answered than just the question of what microcontroller to use. To some extent, we will be touching upon some of these characteristics as we move forward through the course. Now, examples of embedded systems in everyday life, right? They are literally everywhere. So, you could start with the kitchen, where you probably may have come across something like a microwave oven or a refrigerator or a toaster oven. Many other kinds of pretty much anything that has electronics and is in the kitchen is some kind of an embedded system. Communication, of course, the very fact that you are viewing these lectures online probably means that you have access to either a computer or a phone. Chances are that you do have a phone, presumably a smartphone, that has a number of functionalities. We will be talking a little bit more about smartphones in a moment, but technically a smartphone is a form of embedded system. Now, of course, nowadays the fitness bands are a big deal, right? Everybody wants to measure how many steps they have taken and various other aspects of that sort. And yes, they do have a positive effect on the well-being of people who are using them as well, right? But yes, they constitute a class of embedded systems. Entertainment, of course, is one of the largest sort of domains where you find embedded systems, starting with, as I have shown here, the earbuds that can be used as headphones effectively, but also things like portable music players. Nowadays, of course, mostly we use phones and in order to actually play the music, but there could be other aspects of it, right? Certain kinds of specific dedicated devices that are only for the entertainment aspects. Automotive is a very large and important part of where we come across and where embedded systems are used on a regular basis. This, of course, is just showing you what the dashboard of an automobile could look like, right? You have a display that shows you things like the range, the current speed, the amount of fuel that's remaining in the tank, the engine RPM, various things that are useful to you. In the past, these were actually dedicated hardware knobs and modules, gauges that would actually rotate, right? Nowadays, pretty much everything is just one display that is controlled by an embedded controller sitting somewhere in the car. But that's only the tip of the iceberg. That's only the part that you get to see. The real, the more powerful way in which embedded systems make their presence felt in the automotive domain is actually to do with engine control, battery management, and various other aspects that are related to either the safety or the operation itself of the vehicle. And these are largely things that you don't even get to see on a regular basis. You don't interact with them directly. Apart from all this, of course, industries and industrial manufacturing is a very large area where people do use embedded systems at various levels, right? So, you will come across a number of examples of these in industrial applications as well. Now, if you look at what has actually driven this large increase in the number of embedded systems over the last, well, it's not just a few years, it's actually been a few decades now. It has been the tremendous growth in semiconductor technology, right? Miniaturization in particular, which has been going on for the past more than 50 years at this point, has made microcontrollers cheap and accessible. In fact, cheap to the point where it is very often easier to program a microcontroller than to build custom analog circuitry. If you go back into the history of control systems, most of the control theory is actually based around analog differential equations, right? And a lot of it says about how you can apply different kinds of control by directly changing certain analog parameters. Over time, what people found was by just throwing in a digitizer, a fast enough A to D and a D to A converter, and doing all your computations in software, you could get much more reproducible results. And that is actually key, right? The whole point is that analog circuits are hard to reproduce exactly. Matching one analog circuit with the next is not a trivial thing to do. Whereas with a digital circuit, you pretty much can stamp them out by the millions and they will all behave exactly the same, right? The next sort of evolution driver of embedded systems has been, it's again related to semiconductor technology, but it has been a huge growth in the types of sensors and actuators that we have available to us, right? There are a wider range of applications, part of it driven by the semiconductor revolution, but on top of that there are also other kinds of sensors that simply did not exist before. And nowadays, of course, there are still a lot of new sensors that are being built, especially in domains like health related, right? Biological sensors that can sense various kinds of different parameters, health related parameters. And on top of that, the third aspect that has made the growth of embedded systems possible is advances in communication systems, right? Especially wireless communication. If you look at it over the past several years, right, there has been a significant improvements in how we can get very low power but very efficient means of communication, either over very short distances or over medium ranges or even over long ranges. On top of that, we also have the wireless communication techniques. We are currently in the 5G domain, so to speak, right? 4G is what most of you probably have, 5G is making its presence felt, and 6G is already on the horizon. Now what do these Gs refer to? It's the generations of evolution of the wireless communication. The important part is most of these are paying more and more attention to the requirements of embedded systems, right. The term Internet of Things keeps popping up everywhere. It was very popular a few years ago, that it's sort of died down a little bit in the sense that people don't talk about Internet of Things right now. Some people talk about the Internet of Everything. The point is that there is a communication revolution that has happened, which basically makes it possible for all these multiple different kinds of small embedded computing elements to talk to each other and exchange information, and that has really changed the way we can even think of using them. So let's look at some key application areas and the kind of impact that we can expect to see as a result of using embedded systems in these areas. One, as I already mentioned, is the automotive domain, right? And over here we have, as I said, we can break it up into different classes. We have certain things like engine control and fuel injection, which are actually critical to the functioning of the system itself. If you don't have a proper engine control unit, it means that you are not burning fuel the right way. In fact, the car probably won't even start. Modern cars typically have several hundred microcontrollers inside them, right? And including in the engine control unit, where even something like how much fuel is to be burnt at a given point in time is typically controlled by some kind of a embedded system. On top of that, there are also safety critical aspects, such as how fast do airbags deploy when there is a collision being sensed, how is the collision being sensed in the first place, right? How should the brakes respond under different kinds of things like anti-lock braking, traction control, all of those are controlled by some form of embedded system, and these are absolutely safety critical. You cannot afford to say, okay, if it fails, it does not matter. These cannot afford to fail. On the other hand, there are also aspects such as the navigation, right? Nowadays, of course, most of us probably use the maps application on a phone, but on the other hand, there are built-in navigation applications directly into many cars. Climate control, the music system, entertainment, all of those are different kinds of things that are also parts of the embedded network that exists inside a car. Healthcare is one of the biggest and most important areas where embedded systems play a very important role. I already mentioned fitness bands and watches, which are very popular these days and play an important role. I mean, it's alerting people to the effects of fitness and to the fact that you need to get more exercise is in itself a very useful application of these kind of systems. But in addition to that, embedded systems also find their role in even more specific tasks. They can be used, for example, for continuous monitoring of things like blood pressure, glucose levels, and various other kinds of chemical aspects of the body, or even physiological aspects, right, the temperature or various other things that might need to be monitored on a continuous basis, especially for patients who are at a are just maybe recovering from a certain serious illness, right. And the fact that these can be built in such a way that they can literally be connected up and left there to run for days possibly, just collecting information and passing it on, makes it very important from the point of view of actually using the healthcare systems. And of course, consumer electronics, as I already mentioned, there are many different applications out here. It could be something from a household goods or kitchen appliance, or it could be entertainment, or any number of other things that you find around the house. So these are sort of some key areas where you will find that embedded systems are actually being used on a daily basis. But what's the impact? What is the use of actually having all of this, right? One of the things is that they allow measurements and control that were not possible earlier. Things like continuous glucose monitoring was something that doctors would have loved to have all along, but was simply not possible until we got to the point where you could have the sensors to detect glucose easily and cheaply enough, and the entire microcontroller environment around it that could basically run off maybe a coin cell battery, or possibly even just from the energy scavenged from movements, right. All of those put together, and also it has to store the data and it has to be able to transmit it out to a storage system that can then be used in order to analyze the data. all of these developments together are what has made this kind of functionality even possible today. Safety, the fact that you can have continuous monitoring and feedback, something like traction control in a car or an industrial automation system where there are literally hundreds or thousands of sensors looking at every aspect of the factory floor, and any one of them can detect that things if something goes wrong. In fact, it is now at a point where, because sensors are so cheap, it is probably it makes sense to have multiple such sensors looking at the same uh, part of the system from different angles or different aspects, and any one of them can be a fail safe, and it's so that it's you don't have the problem of a single point of failure anymore, and you can coordinate across multiple sensors in order to optimize various costs or to ensure safety of the system. And in general, what has happened as a result of embedded systems being developed over the last several years is an overall change in user experience, right? Even if you go down to something like a kitchen appliance and you have a microwave oven that is capable of just adapting the um, power level or the amount of cooking time based on what it has sensed about the food that is inside it, or if it can automatically detect if something is overheating and shut things off before it goes out of control. All of those are very useful user experience improvements that were possible over the last few years. So, with all of this in mind, I am coming back now to the idea of what we meant about the general purpose versus the specific or the custom, right? And general purpose computing or general purpose computers are what we are most familiar with if you have used something like a laptop especially, right? It's capable of running applications. The most common applications you probably use are, well, a browser. These days it might even be just a browser, because a browser can do everything else for you, right? Chances are, of course, especially if you are working with any kind of documents or programming, you have used some kind of editor or word processor. You are almost certainly checking mail and other kinds of messaging, but that's very likely to be currently inside the browser itself. Having said that, it is an application of its own, right? And there are various other things that actually happen out here, playing music, watching videos, things of that sort, that are actually programmable into the system, right? The other thing that you notice about a system like this, a general purpose system, is that the interaction methods are also very generic, right? There is a keyboard which pretty much allows you to type in anything, any command or any data that you want into the system. There is a mouse that basically allows you to sort of navigate around the screen. The screen itself is used as a sort of feedback mechanism that tells you what the computer wants to convey to you, right? The keyboard and mouse are sort of in one direction from you to the computer. The screen is the reverse. The key part of a general purpose system, of course, is the fact that it is programmable, right? It could be that you as the end user directly program it, and hopefully as students of electronic systems course, you are trying to program your own laptops and computers. But even if you are not programming it yourself, you might be loading other kinds of software or applications onto the system in order to get it to perform different kinds of behaviors. Now, contrast this with a custom system where what we have is a fixed functionality. The example, once again, the microwave oven or washing machine, household appliance, is a good example of that, right? It has a set of predefined tasks. At most you might have a few different cooking levels that you want to change between, right? And that's pretty much all that you are allowed to do. You can't, for example, check your email on a microwave oven. Maybe at some point you might be able to, but not right now, thankfully. There's a limited amount of interaction that you can do with this, right? There are things like keypads and push buttons. So a microwave oven only requires a very specific kind of thing. You need to be able to set the amount of time for which you want to cook something. A washing machine, you just want to choose what washing cycle you want, right? So a calculator, in fact, is a good example of an embedded system that you are probably used at some point. And a calculator has a very specific functionality. It just has a set of numbers and it has a set of operations, and that's all that you can do with it. Of course, the point is people do extend calculators. There are so-called programmable calculators that are, in general, right, they have the ability of actually taking in a program and executing it as well. Now, most of these do have some limited amount of software programmability. You might have come across at some point things where you get what's called a firmware update, right, and it says, okay, your TV needs to update its firmware, or your washing machine needs to update its firmware, and there's a new washing cycle that they have discovered that will clean your clothes even better, right. Now, firmware is a term that is used for things, for it is software, right. The bottom line is it is software, that's no argument about that. The point is, it is also not as easy to modify as regular software. You can't just download new firmware easily. Somebody has to create it specifically for the device that you are trying to update. It can't just be something that people build as a package and release on the internet and everybody downloads it and runs it. No, it has to be something which is very specific to the device that you are trying to update. So, which is why firmware is a term that is used for this, which lies somewhere between the software, which is completely programmable, and the hardware, which is pretty much assumed to be fixed. You don't have a choice in that. And firmware is used in order to customize the behavior of the hardware, but in a manner that is less flexible than generic software. So, all of this ultimately leads us back to this thing of what is embedded within a larger device mean. Right. Now, having talked about all of this, we have a bit of a dilemma here. What do we do with smartphones, right? Smartphones are often mentioned as an example of an embedded system. Why? Well, there are a number of reasons. The actual core functionality of a phone is a fixed functionality, right? You need to be able to communicate. So, every smartphone, the very basic minimum that it has is it has a modem whose job is to connect you to the nearest cell phone tower, right. And there is some kind of standard fixed functionality in there inside the modem which says, okay, if this is a 4G phone, then this is the kind of protocol that it needs to follow, this is the kind of signaling that it needs to do, this is how it connects, right. And that shouldn't be changed, it cannot be changed easily and it shouldn't be changed easily. It can't be that you just download a new package and it somehow messes up your phone or changes things. It has to be pretty much under the control also to some extent of the provider, the network provider. So, this part of it is very sort of restricted in terms of what you are allowed to do with it. Similarly, there are also a bunch of sensors, for example, the tilt sensor, the touch screen sensor, possibly a temperature sensor, maybe an IR infrared sensor, right. Various kinds of things of that sort are also usually baked into the smartphone and are used for various purposes. The kind of interaction you have with the smartphone is also somewhat limited. Older phones which are nowadays sort of making a comeback, you might come across these things called feature phones. They tend to have a keypad with just the numbers and maybe a few other buttons on them. Generic smartphones usually try and have a touch screen, which is a very generic kind of interface, right. A touch screen allows you to display almost anything you want on it, and including, for example, a keyboard. So, you could potentially have any kind of interaction using the touch screen. So, the touch screen once again is no longer that clear why this is a fixed functionality. And there are aspects of the smartphone that actually require real-time response, right. In particular, the entire communication aspects that we talked about over here do have specific requirements which mean that they need to be able to respond in real time, otherwise you actually lose connectivity and you may not be able to manage overall communication system. So, from all of these aspects, a smartphone can be thought of as an embedded system. But at the same time, most smartphones these days are usually running a full-blown operating system. The majority of them at this point in time are probably running Android in terms of numbers. The other most significant operating system is of course the iOS, the iPhone. But there are a few other operating systems as well that are rare but may be used in specific circumstances, right. The point is, an operating system is a much more general thing by itself. What it allows you to do, among other things, is that you can also program the system. You have applications that can run on it. So, you have an app store or a play store that allows you to download and run applications that have been designed for a very generic kind of smartphone, and As long as your smartphone meets certain requirements, possibly in terms of the OS version that is currently on it, you should be able to run the software on it. They have very broad computing capabilities. Most Android phones can actually run a full-blown Linux desktop because after all the kernel, the core of the operating system is actually Linux in an Android system. And it is possible to have almost like a full-blown desktop environment running on a phone and possibly even being displayed onto a larger monitor outside. On top of that, if you look at the raw computing power that is there in the chip in a smartphone, today's even mid-range phones are far more powerful than what would actually classify as probably a supercomputer in the 1980s, right. These phones also typically have operating systems which are not very restrictive. They in fact have the concept of a file system where you can actually store files and documents. They allow access to the network and so on. Okay. So with all of that in mind, this whole idea is a smartphone and embedded system is not a very easy question to answer, right. And well, the bottom line that at least as far as I am concerned, the way that I look at it is, it's probably not a very important question either, right. If there are aspects of it that are embedded, yes, you need to look at it in terms of an embedded system. If there is a real-time constraint, or if there is a power constraint, or if there is some other thing that requires you to program it in a certain way, you need to take those aspects of it into account. Whereas if you are interested in developing general purpose applications, you can ignore all of that and treat it as a computer as well. So with all of this in mind, right, and having seen that there are very specific kinds of functionality that you expect out of an embedded system, let's also look at some requirements of embedded systems, right. And the first and foremost in some sense is a series of limitations. Effectively, an embedded system is putting limits on what you can do, right. There are typically tight constraints on the kind of computing resources that are available to you. You do not have a very powerful processor. The memory available on most embedded systems is typically very limited. In fact, we are used today to laptops with gigabytes of memory. In embedded systems, you can still think of systems that are talking about kilobytes of memory. In fact, there are things with even less than a kilobyte of memory where you can do useful work, right. And that actually turns out to be quite hard and challenging for most people because you are not used to writing programs in a way that require very small amounts of memory. The number and type of interaction mechanisms are limited. Maybe you have only a keypad, so you can't really get all arbitrary characters being entered, right. There might be space constraints. You have only a limited amount of space available to you on a fitness band, right. You can't make it very big and bulky, and you also need to run it off a battery. So given all of these constraints, you have to somehow have something which can work within these constraints and still deliver useful functionality. There might also be certain requirements such as interactivity, which especially and something like guaranteed response times. This is especially important for safety critical systems, right. The anti-lock braking and airbags are the most common examples that usually come up. And of course, we also have the notion of continuous operation, that is, these are literally working 24/7, right. A watch is not expected to be switched off or shut down after a while, you just keep it permanently on. So what all of this means is that the kind of optimizations that we do over here, unlike optimization on a general purpose processor, where primarily we would probably be interested in speed, how fast does a program run, over here there is a notion of something else that can be called efficiency, but also needs to be defined a little bit more carefully, right. And you have some notion of efficiency. Is it in terms of battery life? Is it in terms of the memory that is required? Is it in terms of the interactivity with the user, the real-time constraint satisfaction? Some notion of efficiency under which you are trying to optimize the performance of your system. So to summarize, embedded systems are things that are usually embedded within a larger device. They are constrained severely very often in various aspects: the resources available, the space, the cost of actually building and selling the system, right. They usually have fixed functionality and very often also have real-time and safety guarantees. And how was this entire thing enabled? Largely by the advances in semiconductor technology, right. And as things stand, they affect every aspect of modern life, and there are like very significant things that have been enabled by the presence of embedded systems that were not possible even like a few years or definitely a few decades ago.